Ladies and gentlemen, please welcome a principal with enterprise applications for Deloitte Consulting LLP, Kurt Mortensen.
Welcome back. So technology and technology innovation has really been part and parcel of our industry, and we've talked about that really all day, especially at our lunch conversation today. So over the next 40 minutes, I'd like to spend a little bit of time looking at what's going on in technology today and really what's out there for the future for our industry and what might help shape or be game changers as we look to how that'll impact us going forward. Joining me are two gentlemen that will have very different perspectives on technology as we go forward, and I'll introduce them now. To my right, Dr. Steve Koonin. Dr. Koonin was appointed as the founding director of New York University's Center for Urban Science and Progress in April 2012. Previously served as the U.S. Department of Energy's second Senate-confirmed Undersecretary for Science from May of 2009 through November of 2011. Also joined the California Institute of Technology as faculty back in 1975, was a research fellow at the Niels Bohr Institute during the 1976 and 77, and the Alfred P. Sloan Foundation, 77 through 79. As the chief scientist for BP, Dr. Koonin was the 7th provost at Caltech in 1995 to 2004. He left there to become the chief scientist at BP from 2004 to 2009, where he developed a long-range technology strategy for alternative and renewable energy resources. Managed the firm's university-based research programs and played a central role in establishing Energy Biosciences Institute at the University of Berkeley, the Lawrence Berkeley National Lab, and the University of Illinois Urbana at Champaign. Please join me in welcoming Dr. Koonin. Thank you. And to my left, Atanu Basu, CEO and founder of IATA. Atanu has 20 years of experience in software and high-tech industries. His entire career has been focused on the conceptualizing, development, selling, and deploying of new and unique technologies. Holds a master's and bachelor's of science in chemical engineering. IATA, the company he founded, which is Sanskrit for the word future, invented and refined the technology for prescriptive analytics over a period of 10 years. Simply put, IATA software can ingest all types of data, videos, images, sounds, text, and numbers, just to predict what lies ahead and then prescribe how to improve the predicted future without disrupting other priorities. Atanu founded IATA in 2003 as a research and development company to combine different scientific and computational disciplines for developing prescriptive analytics software. IATA was incorporated in 2009 to commercialize its technology interventions. Please join me in welcoming Atanu Basu. So each of our guests will offer a little bit of a perspective and their views on technology and its influence, and then we'll go into our normal Q&A session. With that, Dr. Koonin, would you like to kick us off?
Sure, that's great. So as you heard from Kurt, my career has afforded me the privilege of watching a broad range of basic science and technology. And so what I thought I would do is to do a lightning tour of the horizon for you, giving you a list of basic science and early stage technologies that I think you in the energy business should be interested in, with something like a 20 to 30 year horizon. So let me go through a list of foundational science and technology fields that are moving rapidly. The first is the info sphere, the ability to acquire data and move it rapidly into knowledge. This is an enabling technology that's foundational for so much of what the world will do over the next several decades. I'll talk a little bit about the nano area, basically inanimate stuff, which is the basis of the physical world that we're working in. I'll talk about the prospects for advance in the bio world, stuff of living things. I will remind you, as I used to remind John Brown in BP, that the energy business is largely about carbon, and all of that carbon came from living things. And so there should be a very natural and interesting connection between biology and energy. And then I'll say a little bit about the neural world, what we're understanding about the behavior of the brain, all the way up to societal behavior. These are the characteristics of the people who use the energy that you're all producing. And then I'll say just one slide about some interesting technologies that I think are on the horizon for energy systems. Transport, power, energy efficiency. So let me start in the info world, and one of the big headlines here is simulation. Simulation to be able to optimize design, facilitate scaling of technologies from pilot to full scale, and to optimize operation. We're seeing now a push to exascale computing from the current petascale generation. Just last week, the Department of Energy announced 2 systems that will hit of order 100 to 200 petaflops in the next few years, and we'll see 100 times current capabilities by 2020. That computing boost in capability lets us put much finer computational grids on things, better parameterization of sub-grid scale processes, and really learn how to do multi-scale modeling. That pretty picture is an ethylene flame, I think, in simulation, and you can see the various reaction products in the 2 different maps. Also, doing simulation rapidly lets us get seriously at uncertainty quantification. We can do many hundreds or even thousands of code runs with plausibly varying parameters or initial conditions and understand better the uncertainty in our simulations. Second major piece is what I like to call the instrumentation of everything. The built environment, the natural environment, and human systems. We're seeing sensors everywhere, on everything, on everyone. My dog even has a collar that texts me every once in a while to tell me where he is. We need to learn how to fuse information or data from multiple sources: text, imagery, audio, geotracks of vehicles and people. Storage and access is an issue. Privacy is integral to this business, and we're seeing advances in that. Visualization, cognitive computing, and applications for monitoring, for efficiency, for compliance. This is one of the major themes in the center I'm working now. And then finally, a big one to watch is autonomous systems, particularly vehicles. The combination of artificial intelligence and robotics together is just going to blow us away over the next decade or 2. You see it most obviously in self-driving cars, but there's much, much more that you can imagine. Second major field, nano. The design of molecules. We're now able to design molecules with fair facility. That little picture on the right is molybdenum disulfide on the upper part of the picture. It's the native material. You can engineer a scaffold, as shown in the lower part, that much more effectively splits water and produces hydrogen. Self-assembly of materials. You can lay down a designed, structured layer on a surface, functionalized in a chemical way, learn how to tune optical, thermomechanical properties of materials, almost molecule by molecule. And then one of my favorites, additive manufacturing. We can build things now layer by layer. That little structure on the right, if you can read the scale bar, it's 2 microns. All right, so a fraction of the width of a human hair. We can make stuff on that scale. We can make it on the millimeter scale. Wonderful possibilities for making things. Third area, biology. If you haven't read up on it, it seems so complicated, but in fact, it's actually pretty simple. There's a list of parts. The parts are proteins. The list is in the genome, the DNA that's in every living cell. We're understanding what the list of parts is, how those parts are shaped, the shapes of the proteins, how the parts work together, and how those networks of parts working together influence what the organism looks like. Just some real-world examples. This is a graph that shows sequencing costs, the cost to read a genome. We're now down at the $1,000 for a human genome and probably dropping even by factors of several in the next few years. So we can sequence anything cost effectively. We're learning the structure of the parts. That molecule on the right, which has many hundreds of amino acids in it, is a channel that lets ions through a cell membrane. We can measure it, we can simulate it. We understand pretty well how it works. This is the metabolic pathway in E. coli, which is the main bacterium in your gut. And Again, it's there just to show you the complexity that we can start to understand how living things function with. And then finally, a real-world example. These are real plants, Arabidopsis, which is a standard laboratory model. On the left is a standard plant going down vertically, subject to 10 and then 12 days of drought, and you can see that the plant dies. If you tweak one gene in that plant in the middle column, you can see that the plant survives very nicely or rejuvenates after 10, 12 days of drought. And then the panel on the right shows two sets of plants that have been made saline tolerant. Again, the salt water kills the untreated plants, but if you tweak the genome, the plants become quite viable in saline solutions. Third one, we'll talk about neuro. Neuro is probably the everyday phenomena of the brain that we just have very little understanding of how it works. We have new tools, microelectrodes, magnetic resonance imaging, optical tools, transcranial magnetic stimulation, PET, that are starting to let us get at the physical basis of brain function. The interesting issues now of what's consciousness, how is memory encoded, things of that sort. That connects nicely to the science of individual behavior. How do we learn? How do we remember? How are habits formed and broken? What is the neural basis of emotion, aesthetics? How do people make decisions? What are the genetic and epigenetic influences of that? There is these days a gene that's been found that's significant at the 5% level in your educational attainment. So if you like, the dropout gene. We will find more and more of that as sequencing goes on and we get better at it. And then there's the whole higher level of human organization in society. What are the networks by which people interact with one another? How do crowds develop and form in the sense of opinions? Okay, last couple words about energy systems. I had the privilege of executing the Department of Energy's first technology review, quadrennial technology review, released at the end of 2011. It's up there on the web if you're interested. Our goal was to survey broadly all energy technologies that the government might be doing research in and identify and prioritize the most important ones. I'll just give you some of my takeaways from that for energy systems. Transport. It's hard to beat advanced internal combustion engines and lightweighting as a pretty solid and cost-effective way of improving vehicle mileage. It's mainly an issue of materials. If we can make carbon composites cheap enough, you can reduce the vehicle weight substantially and effectively double the mileage. It's really a question of how much do you want to pay for the mileage. I think we're going to see a progressive electrification of the light vehicle fleet beyond that. A lot of it's going to depend upon batteries and how cheaply those get better. We'll go a progression from hybrids to plug-in hybrids to maybe, if you really want to, full electric vehicles, but I don't think we really need to do that. Fuel cells are another contender in this. As you may have seen, Toyota just announced a fuel cell passenger vehicle. I think the problems there are the infrastructure for fueling and where you're going to get the hydrogen from. Another market for natural gas, perhaps. Natural gas to power vehicles directly. For fleets, wonderful. For passenger vehicles, again, an infrastructure problem. Biofuels, as was already said today, first generation, not so great. Second and third generation, more promising. In the vehicles themselves, I think we're going to see a lot of action in vehicle-to-vehicle and vehicle-to-grid and in autonomy, as I've mentioned already. In power, we need to drive down the cost of solar balance of systems. Modules have come down already. We need to optimize wind. Turbine-turbine interactions are turning out to be a big issue. Deep geothermal, which connects to your businesses a lot, is in many people's eyes, but I don't see the economics for it. Small nuclear is on the government's radar screen. The government is funding a couple of small modular nuclear reactors at the 50 to 200 megawatt electric class. We need to learn how to extend the life of existing nuclear plants. Fusion, I've got a lot to say about if anybody asks me a question. And then the grid, has already been mentioned today, water is a big deal as we think about power in the future. And then finally, stationary efficiency, a lot of gold to be had there. How we instrument and manage buildings, how we retrofit them, what are the market barriers to building efficiency improvement. With that, I've just about run out of my time, so we'll get to questions and comments, I'm sure, in due
We
course.
certainly will. Thank you very much, Dr. Coonan. I'm going to switch gears from that look, which is very much futuristic, to Atanu Basu, and talking a little bit about what we're doing today with some of the technologies that exist and very specific to the oil and gas industry. So, Atanu, tell us a little bit about IATA and sort of what it's all about.
So IATA started as a scientific research project. So we have been doing the same thing about last 10 years, and nobody cared until like a couple of years ago. 5 years ago, the state of Texas invested to commercialize the research. The technology has nothing to do with oil and gas, but it's finding a lot of applications in oil and gas. And the big idea was, maybe looking back today, was kind of obvious, that we are using data to make decisions, but when we think about data, we think about numbers. Numbers are things that fit in a row and a column. A lot of you are carrying a book by Zuckerman here. Think about that. You can't fit that in a row and a column. You're exchanging a lot of data in that conference. Can't fit that in a row and a column. The idea was, big in big data is not numbers. It's videos, images, sounds, and texts. More than 80% of the world's data today is unstructured. So if you know everything about your numbers, good news. You know 100% about 20%. That's still 20%. How do you use all types of data to predict what's ahead and prescribe how to take advantage of what's ahead without disrupting your other priorities? Give you an example. Dr. Coonan will have to catch a plane, and he will leave after the session. He'll be driving in Houston downtown. He looks through his windshield, sees a car slowing down in front of him. He hits the brake. He gets hit by the car behind you. So his foresight preempted an accident, created another in the process. So foresight is great as long as you can understand your dynamic surroundings, what's ahead of you, what's behind you, what's around you, and as it keeps changing. So that technology came to be known as prescriptive analytics, and IBM and GE started talking about it. So doing the same thing, we suddenly got a lot of popularity. Our initial customers were usual suspects, Microsoft, Cisco's, Dell's, Junipers of the world, who knew about the research and used the technologies to solve multiple problems that we didn't know anything about. Field service, customer service, B2B interactions, retail operations. We found oil and gas about a year ago. Some of our customers, EOG, Chevron, Apache. The reason we like oil and gas, it's the ultimate problem, right? It's the ultimate prize. It's the $8 trillion industry globally. And as we will talk about, it's the ultimate data set. What's happening in oil and gas is Mother Nature meets Internet of Things. Mother Nature is G&G, geology, geophysics, petrophysics, things that the industry knew a lot about. As Dr. Coonan pointed out, now there are going to be sensors in everywhere and everything and everyone measuring anything and everything. And that is creating a new streams of data that the industry wasn't ready for. My stupid smartphone can take video better than ever possible in the history of humanity. And what is that? A sensor. How do you analyze that? I will give you an example of one of those data sets. If you would please play the video. So this is a downhole camera monitoring fluid flow. 11,558 feet, oil, the dark globules that are coming out are oil. You can look at it, you can tell a lot of oil is coming out. That's not that useful. Now let's see what algorithms do to that same video output. It is drawing green boundaries across the dark globules and reporting at the top left how much oil is coming out as a function of time. So you took subjective qualitative data and you made it actionable, quantifiable, something that you can combine with other things. And the technologies that made that possible are computer vision, image processing, and machine learning. And they're just one data set. This is how a Google car drives itself. Dr. Coonan was talking about autonomous car. The car can see, it can hear, it can understand, it can decide, it can act without a human being involved. How does it do that? It has a central nervous system that combines the scientific disciplines that were not designed to work together, to offer functionalities that were never possible. Those type of technologies will come to oil and gas, with or without IATA, because the prize is that big, and 60%, as we will talk about, of the frac stages are ineffective according to data 2 months ago. So think about if you were in any other industry and 3 of the 5 products you produced were broken. You wouldn't be in business too long. That's the status quo in some of the shale completions work today. So since we have been at a long time, we have 20 patents. Even the phrase prescriptive analytics that IBM and GE brag about, if you go out, look up uspto.gov, it's actually our trademark. And it shows the name of our research for a minute.
So what are the key applications of prescriptive analytics, that IATA would bring to an oil and gas company?
So I'll talk about 3 applications. But truth be told, we did not find these applications. Some of the customers I showed and some of the customers I didn't show, they found those applications for us. So I would love to take credit for their stuff. But one is unconventional onshore. We talked about shale completions. Baker Hughes data, 60% of the frac stages are ineffective. So you have a 2-mile lateral, 2 to 3 miles, that is broken into stages containing clusters where you are pumping sand, water, and other chemicals to stimulate the rock to release oil and gas that you are capturing. And if you have pumped all the sand, pumped all the water, and it didn't produce what you expected it to, you say, it's bad geology, and you move on. And you hear in the oil and gas industry, everybody talks about it's all about the rock. Not necessarily. Yes, it's all about the rock, and it's about what you were doing to the rock, and it's about knowing what you were doing to the rock is working as you intended it to, and it is not. And as you have fiber optic sensors and others, you see those applications. So just for completions, there are over 1,000 variables that affect completion. More than 550 of them are actionable, things you can do something about for drilling, production, completion. About 400 of them describe the reservoir. The unconventional reservoir that's not directly actionable, but you are making it actionable by changing the effective porosity and permeability. And over 115 of them that you can set, and I will show a demo about that, to just affect completions. So that's one application. Other 2 applications are both onshore and offshore and conventional and unconventional. This concept of artificial lift, electric submersible pumps that suck oil out to the ground. According to GE, there are 130,000 of those pumps. 60% of the global oil production goes through those pumps. So 54 million barrels a day goes through those pumps. The problem with those pumps, they fail without notice. And what happens when a pump fails? No oil. So the industry fights it in a very reactive mode. So what we were able to do, and the pumps are heavily sensorized, we said, take the pump, put it in the middle of a conference room. It will never fail. The pump is failing because of the fluid going through it and the subsurface in which it's operating. So if you model the 3 together with sounds, images, videos, text, and numbers, we were much more accurate in predicting that. And the other is obviously drilling, non-productive time, invisible lost time. Those are 3 applications that customers found for us.
Right. So let's take shale completions. Obviously, in the tighter economic situation, costs rising and whatnot in the industry, how do prescriptive analytics specifically address some of the challenges, economic, performance, and others associated with shale completions?
So shale completions to us is an ultimate big data problem. So if you take shale completions and look at the data sets, thousands and thousands and thousands of files, and we'll show you an area in Eagle Ford shortly, and you divide the data sets into the types, images, videos, sounds, text, and numbers. You have seismic, mud logs, well logs, microseismic. What are they? They're basically images. We showed a video of downhole fluid flow. You have fiber optic sensors that can measure temperature, strain, pressure, sound every feet, every second along a 2-meter lateral, 2-mile lateral. You have completion procedures, course analysis, which are text. You have production data, artificial lift data, which are numbers. How do you put all of that together to improve completions? If you would please play that video. So this is 3 counties in Eagle Ford, about 400 wells. The ones in red, they are graded in terms of production performance over 60 months. So red, not good; yellow, better; green, really good. What we are trying to do, we're trying to recommend settings to complete the wells before they're drilled. All you're doing is playing with the computer. So you take a well, and it's custom. The shirt that fits me won't fit Kurt, and vice versa. So on this panel are the actionable settings for the biggest influencers for that particular well in that particular geology, Area 6, well 400. The next one should be non-actionables. These are the ones that describe the reservoir, Mother Nature, for that particular location where the drilling and fracking is about to go on. Economics, of course, under the current oil prices, everything is about how much it costs. What you are seeing on the right in purple are what the operator would have done without us. In green, what we are recommending they do. And we are seeing much better performance for each of the wells that they gave us, where we were able to prescribe a set of completion settings, taking into account the geology for where the well was going to be drilled. But if the operator didn't like ours, it has the ability to make some changes and see how it would affect cumulative production over 60 months, estimated ultimate recovery over the lifetime of the well, net present value, rate of return, PV10, and under current economic conditions, those are big. So you may decide not to do the best well, but do the best $6 million well. Do the best $5 million well. So the language is changing. So you see the capability to optimize based on what you care about, depending on how you are funded, private equity, or you go to IOC or NOC, it doesn't care. This is the ESP application what we talked about. Not only the pump, take the fluids going through the pump that contain corrosive material sometimes, and the geology, and that's how you can predict a pump failure and prescribe either a planned outage or modifications to extend the lifetime of the pump to get more oil out. And it's onshore and offshore both.
Thank you, Atanu. Appreciate that, and Dr. Coonan for your comments. We'll go to the audience for questions. I'll kick it off though with maybe a couple. I'll start with you, Atanu. How have you found the adoption, of prescriptive analytics within the oil and gas industry? Are they fast followers, leading edge? Have folks wantingly taken this on?
Not really. We were talking past each other. So we were talking our Google-like technology language, and they were saying, don't let the door hit your ass on your way out. I have no idea what you're talking about. And we were very disappointed because we thought we came really prepared to talk to these guys. And now we don't talk about computer vision and machine learning and natural language processing. We say, your production per stage in that well is 30% different from the well in a similar geology. How are you addressing that? We say, oh, we have a black box thing that we're going to look at your data and give you a setting. Try it our way for 5. Try it your way for 5. Let's see what happens. I mean, if we cannot help you, what we do doesn't matter anyway. Instead of trying for 6 months and 9 months, going nowhere, trying to talk about how Google Car works. It's good in a conference. It's not good in a customer setting because they cannot put the 2 and 2 together. Right. And they are together. It's the same, science doesn't change.
Great. Dr. Coonan, to you, if you looked out, I think it took a 30-year horizon and really looked at the science and technology that might influence our industry, what's the one thing you think you can, is a sure bet to have probably the most impact on oil and gas?
Yeah, so, I think all of the 4 fields I talked about, materials, biology, neuro, which is about the people, will have an impact, but the datification or the instrumentation, you heard it from both of us, it's the data everywhere, from everything, and learning how to make sense of it. It will affect us in our everyday, it's already affecting us in our everyday lives, but I think you'll see it more and more in the business world as well.
Great. All right, let's turn to the audience. Are there questions? I see several hands in the back.
So one question that I have is, what parts of the industry do you think will see the biggest impact? And Dr. Coonan, this might be for you, and from the science and technology that you talked about. And is there anything that would keep it from having that impact?
You know, the E&P, when I was in BP, of course, seismic was king, and they spent a lot of time and money trying to understand subsalt and all of that. I think in 5 years, we'll be able to do that even better than we can do now. I think onshore, you're going to see new methods of using ambient seismic, for example, in exploration. Reservoir management, which is a little bit about what we were just hearing. Also, you're going to see that. My guess is that refining is already pretty well optimized. It's a smaller system. It's already been pretty well instrumented. So I think in the E&P is where you're going to see the biggest impact.
Other questions? See a hand up front here.
Oh, retail. There's probably, I don't know if anybody's in the business in retail here, but you know, customers understanding how to target advertising, that's going on big time, not only by the stores, but by the political campaigns. The insurance companies want to stratify risk, and so they're finding out about people and how to influence them as well.
Sure. Ma'am?
My question is for Atuna. What have been the challenges you faced in really implementing your processes and realizing the value?
Realizing the value?
Yeah, or what are the challenges? What could prevent you from really attaining all that you want from implementing a process like this and going to prescriptive analytics?
Initially, we didn't know what to ask for. We were, as I said, we were talking past each other. Now, we have a complete framework of the data sets we need for the 3 problems we described. So when they give us data, which is a very confidential, private thing, and it's a pain in the butt to get to, but when we get it, we can easily verify it and say, okay, they gave us what we needed, and we should be able to produce initial results by doing a couple of runs. And initially, we were not doing that, so there was a lot of back and forth. Oh, I thought I gave you everything. No, I didn't really get that. And it was, looking back, it was more that we didn't know what we were doing. It's not the customers. It's like our job to communicate, and we were not. We were not listening.
Thank you. Other questions? Tomas?
Steve, you open up the question, so I have to ask it. You mentioned fusion, say somebody asked me, I'll talk about it. Let me phrase the question around fusion energy. When it arrives, is it going to be too late? Is it going to have an impact?
Too late for what?
To change the energy system as we know
If
it.
we're interested in reducing emissions, for example?
Yeah.
Probably, yeah. Too late. Look, as you know as well as I, the world or the U.S. are pursuing 2 main routes. One is something called ITER in France. It's now a $40 billion project. Won't see first plasma, I've heard, until 2027. You'll run it for 10 years, and then you got to build another one. So I don't think, if everything works well, you're not going to see power into the grid until 2040, 2045. The world's going to run mostly on fossil fuels up until then. The other way of making fusion is inertial fusion, probably comparable timescales. So, you know, energy source for the future, as it always has been. But we're making progress scientifically. I mean, you have to realize power's a commodity, right? And it's not just that you can make it work, but you got to make it work cheaper than everything else, or at least in the same ballpark. Very far away.
Great. Thanks, Tomas. Other questions?
Yes. This question is for Steve. You talked a little bit about sensors, and we hear a lot of discussion about the Internet of Things. So I'm assuming the sensors would be part of that. Can you talk more about how that could be applied to the oil and gas industry?
You know, imagine that you could sprinkle seismic sensors everywhere, right? Not only when you're doing exploration, but as you're managing a field. I could use the ambient seismic to probably get a pretty interesting picture of what's going on, much denser than we do now, for example. I mean, we saw an example of the video downhole. You can imagine much more of that. I want to know temperature, pressure, composition, flow rate, geometry in a producing well. If I'm doing exploration, a sensitive gravity meter is something people are trying for. I mean, these are not sensors everywhere, but very sophisticated sensors, right? Methane, if I can detect methane leaks, I'm halfway home to finding new sources, right? So it's very interesting to just think if I can measure anything, what do I want to measure and what it could tell me. We're almost at that stage now.
Tano, you may want to weigh on that.
Yes. One way to look at it is Internet of Things is already here. What is microseismic? What is a downhole camera? What is a fiber optic sensor? What is a tracer? And they are being deployed in mass scale among the large independents and the IOCs and the NOCs of the world for all fracking operations. They are sensors. They're collecting data, sending it back real time or batch. And what they're telling you is what you are doing to Mother Nature, is it working according to the plan? And most of the times it is not, and that's why we have this inefficiency. We call them the other secret of fracking. It's a very inefficient process. And sensors are the only way that we would know. If a company like EOG would have a 16 to 22% EUR, and the rest of the industry would have a 5 to 6% recovery factor. Why is that? You have operators in similar geologies next to each other, the 30% performance difference. Why is that? So Internet of Things, or another way to look at it is the industrial Internet of Things, which, as Dr. Kurin is saying, is going to be the future, but they're in there right now reporting on your performance or lack thereof.
I think it's also not only at the industry end, but at the consumer end. My house runs on both propane and heating oil, and I want sensors on those tanks that will tell my supplier, hey, it's time to come fill me up, or tell me how many days I've got left. I mean, lots of little examples like that, none of which are rocket science, but you can imagine how they could change things if done on a large scale.
That's great. Good questions. Any others from the audience? I see one. John?
Yeah, this is kind of a wide open question for either of you, but I guess I think back to 10 years ago, nobody saw this shale revolution coming, and we all have gone on in great depth today about how it's changed the world. What are we not seeing today? That's an easy one for you, but I thought I'd throw it out there.
Yeah. I was going to ask you first.
Okay.
Unknown unknowns.
Yeah, so I'll piggyback on what he said. Known, unknown, unknowns. And I think we're in the middle one, known unknowns. So as more instrumentation is going into these wells, you are seeing which rock was stimulated, which rock wasn't stimulated, how was it stimulated, what is coming out. You have a Joule-Thomson effect and others that can tell you how much gas, how much oil. So XYZT. XYZ is the location underground, T is the time. Think about framing this shale problem or the shale opportunity in terms of XYZT and knowing what's happening in every XYZT over time. And that's why it's an ultimate big data problem and it's the ultimate prize. What we are seeing is some of the fiber optic pictures that you will be able to see, even go to Halliburton's site or Schlumberger's site or GE's site. And they will show massive areas are unstimulated. So if they have 36 stages, maybe the production is coming from 4 or 5 of those. But they think all the 36 stages, it's like if all of us wore the same size shirt, I will look ridiculous in his shirt, he will look ridiculous in mine. But that's what they're doing. All the treatments are similar along the 36 stages. And obviously it's not working because one size doesn't fit all in different geologies by different operators, different energy services companies, different frac fluids, different sands, different proppants, and different Mother Nature and different capabilities of those energy services companies. So what you were seeing, you will see a lot of these pictures validating the problem that I'm qualitatively mentioning.
So I'll try a very different tack. One of the advantages of being a professor is you can talk about things you don't know anything about. Some people sometimes believe you. Not your business directly, but something that will affect your business. Think about how not only communications, but these big data techniques can change the way in which society does its business. So suppose, for example, that some of the anti-fracking NGOs had the marketing capability, the big data capability to just go out and organize in a much more effective way than they have been now. We can argue whether that's a good or bad thing, but it could certainly affect the business that you're all concerned about. So I think the ability for society to regroup and form pressure groups and change politics is probably something that's going to be more prominent over the next decade or two.
Our time is up. Please join me in thanking our two speakers this afternoon. Thank you, gentlemen.
Thanks, guys.